afternoon. My name is Walter Salas.
Armando Camacho.
Sami, Awad.
Orangel, Velasquez.
And today we'll be talking about the analysis and synthesis of mechanisms. To start with, we'll be studying the mechanisms of 4-bar in order to maximize a desired motion which directly depends on the application. A numerical procedure will be developed to analyze the required specifications such as velocity, position, and acceleration. Also, a computer simulation will be designed in order to visualize and get a more detailed analysis of the desired criteria. Finally, a crank slider mechanism will be synthesized. Historical perspective of mechanisms. The story of the development of the geometry of motion is composed of time involvement in dynamic machines, mechanisms, and how mathematics can describe their kinematics. Starting in the 1500s through the Renaissance era, machines were considered to be constructed from simple mechanisms. With technology moving at a fast speed and working together with engineering, we've been able to develop the technology to achieve better performance in all aspects in the past few decades. Analysis of a 4-bar mechanism. The mechanism analyzed is commonly known as a 4-bar mechanism. It represents one of the most common mechanisms and is widely employed in many industries, such as construction, automotive, aerospace, and manufacturing.
The constraints and objective of this project, at least for the 4-bar mechanism analyzed, the first one is that theta 1 had to be fixed at 5 degrees, and the linked lengths of link 2 and link 3 were giving us 20 centimeters and 65 centimeters. The input link 2 is supposed to rotate from 0 to 360 degrees. The task for this project is to analyze the position, velocity, and acceleration of each of the links, and using the two possible closures of this mechanism, obtain and maximize the motion of link 1 and 4. Now, the mechanism analyzed was the application for this mechanism was chosen as an artificial ocean wave generator. This mechanism will go through its entire motion, displacing a blade which is connected between the two 4-bar mechanisms, and the blade will displace a volume of water inside this channel. Now, the water that was displaced inside this channel will actually go out and will displace other water outside, creating the wave. And the motion will get intensified as the velocity of the mechanism, the angular velocity of the mechanism is increased. So here you can see the results of the analysis of one of the 4-bar mechanisms on each of the sides. And the position analysis basically yielded the two linked lengths that were missing, which was link 1 and link 4. These mechanisms were found to be 45 centimeters and 50 centimeters. And the range of motion of the rocker goes from 55.2 degrees for theta 1, for theta 3, and 73.4 degrees for theta 4. And these are the equations we use to find for the first closure of the mechanism, the position. So here you can see the two graphs of the angular velocity of link 3 and link 4. Link 3 had a maximum angular velocity of negative 8.49 radians per second. The negative just means that it's spinning clockwise. And link 4 has a maximum angular velocity of 10.44 radians per second in a counterclockwise direction. You can also see the formulas that were used to obtain these results. So lastly, we did the acceleration analysis. You can also see the graphs of the acceleration of link 3 and acceleration of link 4. And the maximum angular acceleration for link 3 was found to be 183 radians per second squared in a counterclockwise direction. And similarly for link 4, the angular acceleration was found to be 114 radians per second squared in a counterclockwise direction, and these are the formulas used for the analysis. This is a video representing the motion of the mechanism. You can see as the links, as the link 2, which is the shortest one, goes through its 360 degrees of motion, the blade gets displaced up and down, and this motion will displace the water inside the channel, which will displace the water that's surrounding the actual wall and channel, creating the artificial waves. And you can see that this motion, the motion of the slider of the link 4 had to be maximized in order to achieve more displacement of water.
For the second part of the project, we needed to synthesize a crank slider mechanism, and they were given 3 points in our system that were acting as a coupler, and they were required to pass through these points. We have A1, A2, and A3 with the respective B1, B2, B3. For one of the constraints on the project is that we have to be able to move these points around to be able to fully develop the collinear system for A, B, and C to be lining up in a straight line and make collinear. So for the position provided for B, the project formulation were given incorrect values of the slider. So we were allowed to be able to move those points by plus or minus 1 inch until the modified mechanism makes physical sense. Here on the chart it shows our original B values that we had, and then we added the new B values to be able to fully develop the crank slider mechanism to be able to pass through those points in a collinear linear system. For the slider crank system, we needed to find the circle slides. To be able to find the circle slides, we need to figure out the pole positions of AO, which is where it's initially holding the crank slider, and the poles P12, P13, and P23. What happens is that with P23, the point is so far outside of the circle slides that we needed to develop, so we needed to figure out a point for P23, the image or the mirror image of P23, to be able to use that point as one of our 3 points in our circle slides, which it's found here. Now with points P12, P13, and mirror 23, we're able to find the center of the circle slides and the radius of the circle slides using a formulation of equation to find the circle based on 3 points and the radius. We also needed to determine for the circle slide the local coordinates for C1, C2, C3. What C1, C2, C3, it's basically telling us that we have a linear motion of a crank slider mechanism that has to be passing at all times. And for that to happen, we need to develop C1, C2, C3. To find C1, we are allowed to pick an arbitrary point within the circle slides that at any point around the circle slides will work as an arbitrary value. Once we found C1, we're able to find out C2, C3. As long as all these 3 points are in the same line, then we're able to fully synthesize the slider crank mechanism. Here in the following chart, we're able to plot the local coordinates for C's, C1, C2, C3. As we can see, all points are almost aligned in the same line, so meaning that our system is fully synthesized, given our values are correct. And here the R square will tell us that our values approximately, they're very close and accurate, meaning our crank slider mechanism will be synthesized and can be used in many types of applications later on.
Here is the slider crank design that has been synthesized from Orange's section. As you can see here, the slider crank motion is achieved by transforming circular motion into rectilinear motion. Angles of link 1 relative to ground agree with the kinematic analysis, and full range of motion achieved with no singular positions encountered. Additionally, the couplers, as previously stated in the objective, pass through all positions in order. Here's a simulation of the slider crank. The application for a crank slider mechanism is using an electrical motor that can be used to drive the input link and drive the reciprocating saw. These saws can be used to cut thin metal sections as well as lumber. They can go from handheld sizes all the way to industrial sized machines. In conclusion, the synthesis of the mechanism showed that the values for B needed adjustments in order to obtain a point that would allow for the slider to move in a straight line as opposed to a circle. The final kinematic analysis verified that the slider moves in a rectilinear motion as the crank is rotated.